Hello everyone, welcome back to solid state series. This is the solid state part 9, and in this video particularly we have to talk about close packed structures in solids. Close packed structures in solids. In fact, in reality all the solids are three-dimensional, but instead of going to three-dimensional solids straight away, in order to understand three-dimensional solids in a better way, first we have to understand close packed structures in one dimension, close packed structures in two dimensions. In this video particularly we are going to talk about the close packed structures in one dimension, close packed structures in two dimensions. So without making any delay, first let us see the actual classification of close packed structures. If you see the classification of close packed structures, so here all close packed structures based on the orientation of constant particles, they are in fact divided into three parts. One is close packed in one dimension, close packed in two dimensions, close packing in three dimensions. In this video, we'll be talking about one dimension and two dimensions. In the next video, we'll continue our topic in close packing in three dimensions. So close packing in one dimension, very clear. The name itself gives the meaning the particles are present only in one direction. In two dimensions, the constant particles are present in two directions, any two directions. So these are further classified into two types. One is square close packing, another one is hexagonal close packing, right? And in three dimensions, close packed structures in three dimensions, we have four different types of close packings. One is a simple close packing, one is a face-centered close packing, hexagonal close packing, and a body-centered close packing. Indirectly, simple close packing, face-centered close packing, body-centered close packing we studied, and one more thing we have, that is hexagonal close packing. So first let us take a close packing in a one dimension, after that a close packing in a two dimensions. And here is the structure for you, and here close packed structures in a one dimension. So here very clear, the constant particles are present only in one direction. You can see only in this direction. There is no particle in y-axis, there is no particle along z-axis. Here the particles are confined to only one direction. I already told you, in reality these kind of structures, solids, are not possible. All crystalline solids are three dimensional, right? And in this, the only point we have to focus, every particle is in contact with the two other particles. You can see, if you see this particle, this is in contact with the left side particle and also right side particle. And here, this number, it is directly in contact with the two adjacent particles. This number is actually called a coordination number, and the coordination number is 2. There is nothing else about what do we call close packing in one dimension, and coordination number is 2. And now let us take a close packing in two dimensions. As I told you before, these are further divided into two parts, two types. One is square close packing and another one is hexagonal close packing. And first let us take a square close packing. Very clear, the particles are present in two dimensions. Two dimensions. Whenever we are in two dimensions, you can see this is taken as the first layer, and these are the particles of a first layer. And here, whatever the places you are seeing here, these places are called depressions. These places are called depressions. So here, these are the depressions. These are the depressions. And in case of square close packing, the particles of second layer exactly in the not in the depressions, they are lying exactly below the particles of first layer. The particles of second layer are lying exactly below the particles of first layer instead of in the depressions. They're exactly below the particles of what do we call first layer. So I can say this is the first layer and this is the second layer. And you can see this is what we call a repeating unit, and we can call it as unit cell. The unit cell repeating unit is a square, hence it is called a square close packing, right? And if you take all layers, so this is the first layer, and here this is the second layer, this is the third layer, this is the fourth layer, and every layer you can see the orientation. So here what do we call the particles are lying exactly below the particles of the previous layer, and if you want to see, these are what do we call repeating units, and these repeating units are called unit cells, and a unit cell is a square. And here, if I say the orientation of particles in first layer is A, that orientation is A, even in the second layer, the particles orientation is exactly same. Hence, we have to say A here, A here, A here. So simply overall packing, if you take this is A type of packing. If you don't like A, you say X type of packing, that is up to you. And according to the definition of coordination number, you can see this particle, you can see this is directly in contact with the four other particles, 1, 2, 3, 4. Hence, the coordination number is 4. But particularly if you observe, every particle is directly in contact with two other particles of same layer, one particle of previous layer, one particle of next layer. This understanding is important. Anything can be asked in competitive examination. Yes, the coordination number is absolutely 4, no doubt about it. But the particle, every particle is in contact with two other particles of same layer, one particle of previous layer, one particle of next layer, and the coordination number is 4. Here, if units and dimensions or radius are given, easily you can calculate what we call a packing efficiency or packing fraction. The definition of packing fraction is the same. So since it is two-dimensional, we have to say area of the square. So here area of all particles by area of the square. If you take that ratio, you will be getting what we call a packing fraction, right? And one more we have, that is hexagonal close packing. In case of hexagonal close packing, please remember this is also two-dimensional. The particles are confined to only two dimensions, two directions, right? And this is the arrangement of particles in first layer. So what I can say is the arrangement of particles in first layer, here the arrangement of particles in first layer is the same. Square close packing and hexagonal close packing two-dimensional, the first layer arrangement is same. The difference is in second layer. In case of second layer, the particles of second layer, instead of lying exactly below, they occupy what we call depressions. So here they are in the depressions of the first layer. Now you can see. So these are the particles of second layer. The alignment you can see. The alignment of particles, they are not lying exactly below the particles of first layer. Instead, they are occupying the depressions of the first layer. And what about the third layer particles? Yes, third layer particles occupy the depressions of second layer. And overall packing, if you see when third row is placed adjacent to the second in staggered manner, it's the spheres you can see. But overall, if you observe the first layer and the third layer, they are, you can see the third layer particles are lying exactly below the particles of a first layer. Alignment you see, alignment I'm talking about, right? Of course, the first layer and third layer are separated by one more layer, but if you see the particles, you can see exactly below, exactly below. And all layers, if you see, this is the overall packing. If I say this is B, depressions are occupied A, again depressions are occupied B, because here the arrangement, alignment you can see. So here, what do we call the first layer and the third layer have same type of arrangement. Second layer and fourth layer have same type of arrangement. Hence, this type of packing is called AB type of packing. And here, what is the repeating unit? So this is the repeating unit. You can see this repeating unit has 6 corners. 6 corners, hexagonal close packing. And at center, of course, there is one particle. And remember, this is two-dimensional, not three-dimensional. And here, every particle you can see, every particle is directly in contact with the 6 other particles. You can see this particle is directly in contact with the 6 other particles. Already told you, we are in two-dimensional. This is layer 1. This is one layer. This is previous layer. This is next layer, right? And every particle is in contact with the 2 other particles. You can see 3 and 6 are coming from same layer. 1 and 2 are belonging to previous layer. 4 and 5 particles belong to next layer. Of course, coordination number is 6, no doubt about it. But if you split this, so 2 from same layer, 2 from previous layer, 2 from next layer, hence altogether it is in contact with the 6 particles. So the coordination number is 6. The type of packing is AB, 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 AB type of packing. And before ending this video, once let us compare. So comparison of 2D packing. So this is square close packing. This is hexagonal close packing. If you want, you can see the unit cell here and here. This is the unit cell. One is a square close packing and another one is a hexagonal close packing. If you compare, very clear, here the void size are number of voids. So void size particularly, if you take, this is square close packing and this is hexagonal close packing. And if you see these, we can see if we compare square close packing with hexagonal close packing, we'll observe that empty spaces are less. Empty spaces are less in hexagonal close packing when compared to square close packing. And based on this diagram, we can simply say the efficiency, the packing efficiency of these two structures, if you compare without any hesitation, we can say that the packing efficiency is more for hexagonal close packing. That is more for hexagonal close packing. And this is about close packed structures in one dimension, close packed structures in 2 dimensions. In the next video, we'll discuss close packed structures in 3 dimensions. And this is the end of solid state part 9. Thank you very much.